Have you ever tried to predict what SpaceX's Starship version 3 will achieve in 2026, whether it's the number of launches or the milestones it could reach? The answer likely depends on one mission. Flight 12, the debut of Block 3. Its success or failure will set the pace for everything SpaceX hopes to accomplish this year. According to a recent FCC permit, the launch could take place as early as April. However, SpaceX may move up that timeline, as a full ship-to-ship refueling test is planned for June. A 2-month window is a tight schedule for the company to take a completely new generation of Starship to orbit and demonstrate part or full reusability, 2 milestones it has yet to achieve. SpaceX also needs to increase the number of Starship launches in 2026 to validate Block 3 technologies on schedule for NASA's Artemis 3 mission, planned for mid-2027. Whether SpaceX reaches its 2026 goals depends heavily on a smooth debut for version 3. This explains the intense interest surrounding Flight 12, which will serve as a crucial proving ground for new technologies. The mission will also debut upgrades to Pad 2, which will later be mirrored at Pad 1, Launch Complex 39A, and SLC-37 on the East Coast. Flight 12 introduces the full Block 3 Starship stack, consisting of Booster 19 and Ship 39. Compared to the Block 2 design, Block 3 offers improved structural strength and greater payload capacity. The booster is essentially a clean sheet redesign, while the ship has been significantly upgraded. This mission will also showcase the Raptor 3 engine, the most advanced engine SpaceX has ever built. The new Raptor is roughly 25% lighter than its predecessor, delivers about 280 tons of thrust, and achieves a higher specific impulse of around 350 seconds. A key objective of Flight 12 is to conduct the final Raptor relight test before the next flight. Flight 13 attempts orbit. This step is vital because version 3 uses the simplified Raptor 3 engine design, which lacks a heat shield. Reliable engine restarts are essential for controlled re-entry and recovery, making this test a critical prerequisite for orbital operations and future payload missions. Another major change is the new integrated hot staging ring. Unlike earlier bolt-on designs, the new ring is built directly into the Super Heavy's forward dome and methane tank structure. This integrated setup removes the need for a separate jettisonable component and includes triangular vents that allow exhaust gases to escape more efficiently during ignition. The result is reduced heat and pressure stress on the booster, a simpler assembly process, and no need for pre-launch installation. The permanent ring integration cuts weight, increases payload capacity by up to 10%, and works in tandem with 3 larger grid fins, down from 4, positioned lower for compatibility with the catching system. Flight 12 will test the full reliability of this system during stage separation. Ship 39 is expected to debut with an upgraded heat shield that introduces a new crunch wrap sealing material. This design helps close small gaps between tiles, improving both maintenance speed and heat protection. Structurally, Ship 39 represents a major shift in Starship's design approach. Starships. Imagine the rocket body as a tall soda can made of metal. The old design cuts the can into short horizontal rings, like donuts. Weld each ring to the one above, charts below it. Lots of circular welds around the rocket equal many weak spots when heat pushes sideways. Instead, the new design cuts one tall rectangular sheet, rolls it into a tube, weld just one straight seam running top to bottom, like a zipper down the side. Fewer welds, stronger because they match the push direction during flight. The new way spreads force evenly, like load-bearing walls in a skyscraper versus just floor joints. These changes matter because the nose cone endures some of the highest stress and heating levels on the entire vehicle. A more robust design increases the likelihood that version 3 can perform as intended under real mission conditions. SpaceX aims for Flight 12, or at the latest, the second Block 3 mission, to achieve what it considers a perfect test flight. That means following a high arc trajectory similar to Flights 5 through 11, reaching altitudes of 200 to 300 kilometers before performing controlled splashdowns. This approach allows engineers to validate Block 3's navigation and propulsion systems under realistic conditions, much like the soft splashdowns of earlier Block 1 and 2 flights in the Indian Ocean. This conservative flight plan ensures clean, high-quality data on the new systems before the subsequent flight attempts more advanced goals like orbital flight, ship catching, and propellant transfer tests. While upper stage Raptor 3 testing will provide critical data for future refueling missions, the upgraded ground systems at Pad 2 are also key to faster launch turnarounds. Flight 12 will mark the first operational use of the newly completed Pad 2 at Starbase. Pad 2 features a new foundation design, a stainless steel framework filled with concrete, unlike Pad 1's traditional concrete base with steel cladding. The new foundation stands about 1.5 meters taller than Pad 1's, likely to accommodate the increased height of next-generation booster stages. Larger doors and improved access points also make it easier for teams to reach internal components during maintenance. The new chopsticks on Pad 2, SpaceX's third set, are about 10 meters shorter than those on Pad 1. The reduced mass improves responsiveness during catch operations, while additional reinforcement reduces flexing during fast movements. These upgrades reflect SpaceX's effort to make each launch pad iteration more durable, efficient, and precise than the last. The Pad 2 launch mount introduces a bold new structural design. Unlike Pad 1's circular donut-shaped mount, Pad 2 features a large cuboid frame with a central circular opening for booster integration. It still uses 20 hold-down clamp arms, but each has been redesigned from the ground up for greater strength and reliability. The top of the Pad 2 mount also features a major advancement involving a fully water-cooled steel plate, similar in concept to the one first tested beneath Pad 1 during Flight 2. This new version is expected to handle the immense heat and force of repeated Starship launches with far greater durability. In another major difference, Pad 2 adds an integrated flame trench, something Pad 1 lacked. At Pad 1, exhaust gases were deflected outward after liftoff from a flat steel plate cooled by upward water sprays. Pad 2, by contrast, directs the exhaust downward into the trench, where a network of high-pressure water jets from various directions rapidly cools the exhaust and reduces noise and vibration. The upgraded deluge system represents one of the most substantial improvements over Pad 1. Pad 2's pumps can deliver roughly 422,000 gallons of water at much higher pressure, with jets positioned not only on the main plate but also along the trench walls, the central ridge, and the plate perimeter. This multi-angle coverage ensures complete protection from the intense thrust of 33 Raptor 3 engines firing simultaneously. Another advantage of the new system is water recycling. Pad 2 can capture and reuse water between test runs, allowing same-day relaunch attempts if needed. While both systems convert much of the water to steam during operation, Pad 2's efficiency and sustainability mark a clear step forward in SpaceX's infrastructure. Anyway, if you enjoyed this breakdown of SpaceX's Starship plans, make sure to like the video, subscribe to the channel, and turn on notifications so you don't miss the next update on SpaceX's progress. As SpaceX prepares to begin regular operations from Pad 2, attention has turned to how frequently the company can fly Starship in 2026. Predictions vary widely. Cautious analysts expect between 3 and 6 launches this year, noting that early test phases often bring delays as new systems are refined. A moderate outlook suggests 7 to 10 launches, with many calling 7 or 8 the most realistic target if progress continues smoothly. Optimistic forecasts reach higher, projecting 12 to 15 flights, roughly 1 per month, assuming no major setbacks. More ambitious models imagine as many as 15 to 20 launches, achievable only if orbital refueling becomes operational by spring, and both pads can support regular flights by year's end. The most aggressive predictions, topping out between 30 and 50 launches, assume full and rapid reusability is proven by mid-year, an outcome that would redefine what's possible for large-scale spaceflight. So, what do you think? How many Starship launches are you betting on for 2026? Let me know in the comment section below. The number of Starship launches in 2026 will depend largely on how quickly SpaceX resolves technical challenges and establishes reliable spacecraft reuse. First and foremost, as said, if the first Starship version 3 launch proceeds smoothly, without major setbacks, SpaceX could achieve 10 to 12 missions this year. However, any serious failure early in the program would likely cause delays and force a reworked schedule. Second, reuse and mission cadence. Reusable hardware remains essential to SpaceX's lunar goals. To support the required number of tanker flights for the Artemis program, Starship must reach a steady launch rate, ideally 1 flight per month or more. Without that cadence, meeting lunar milestones becomes unlikely. Production capacity will also play a key role. If the company cannot implement rapid reuse quickly, the rate at which new ships are built could limit progress. A successful first flight of version 3 would clear the path for recovery and catch attempts on subsequent missions. Successfully catching both the booster and the ship would mark full-stack reusability, removing major hardware bottlenecks for the rest of the year. Infrastructure and manufacturing. At present, Pad 2 at Starbase, Texas, is expected to be the primary operational pad through 2026. The pace of launches will also depend on when Pad 2 reaches full readiness, when Pad 1 completes refurbishment, and when Launch Complex 39A in Florida comes online. Despite these logistical challenges, vehicle availability is unlikely to hold back the program. SpaceX's Star Factory already houses at least 10 ships and 3 boosters in various stages of assembly, suggesting that production can support a busy launch schedule once reusability is proven. SpaceX has set its sights on one of the most demanding goals in aerospace engineering, building a fully reusable Starship system. At the heart of that plan is Mechazilla, the massive launch tower designed to catch both stages of Starship in mid-air. The idea sounds almost impossible. Catching a rocket still moving under its own momentum leaves no room for error. A mistake here would bring consequences far worse than anything seen in Starship's first flight. So far, though, things have gone surprisingly well. SpaceX hasn't yet suffered a failed catch attempt. In fact, the company pulled off its first booster catch on the very first try with the version 2 vehicle. The upper stage, however, remains a different story. SpaceX hasn't attempted to catch it yet, not because of hesitation, but because early Starship variants had issues that made such a maneuver too risky. Problems like uneven ascent performance and heat damage to fragile ceramic tiles during re-entry made precise tower alignment unsafe. Version 2 of Starship isn't the final design anyway. SpaceX is now developing version 3, a more refined model paired with a brand new Launch Pad 2 built specifically for the next generation of vehicles. Together, these upgrades in both hardware and ground systems will make it possible to attempt safe upper stage catches, especially for missions that need rapid reuse to reach deep space. Launch Pad 2 represents a major leap over the first design, particularly in its actuator system. For those unfamiliar, an actuator sits between the chopstick carriage and main arm, controlling 2 key functions: opening and closing the arms horizontally and absorbing the shock when catching a vehicle. Managing that impact smoothly is critical. Any abrupt transfer of force could damage both the rocket and the tower. The new actuators feature more segments and a larger end section than their predecessors. SpaceX replaced the older versions after testing revealed limitations. They couldn't push hard enough, move fast enough, or stop cleanly without bouncing. Engineers solved this by upgrading the hydraulic pumps to deliver steadier fluid flow, giving the arms more strength and precision even under the immense weight of a returning rocket. Faster accumulators were also added to improve response time. These components store and release fluid under pressure, allowing the arms to close in seconds during a catch while staying stable. Meanwhile, upgraded servos, the fine-tuned muscles of the system, now use smarter sensors to align perfectly with the rocket's guide pins, ensuring smooth, accurate catches that protect both machine and mission. Another major change on Launch Pad 2 is the design of its arms. They're about 10 meters shorter than those on Pad 1. That reduction in length may not sound like much, but it makes a big difference. Shorter arms mean less inertia, which allows them to move faster and with greater precision. Combined with stronger internal reinforcement, the new design gives SpaceX better control in every motion, raising, lowering, opening, or closing, making the system quicker and more accurate when catching a returning Starship. Safety and automation also take a big step forward. On Pad 1, the quick disconnect fittings, essentially the large plug-and-socket connectors that feed super-cold fuel into the rocket, were mounted high up the tower. Crews had to climb into hazardous zones to connect them. Pad 2 fixes that problem by moving the fittings lower and automating the entire process. Now, the chopstick arms swing the connectors towards the rocket on their own. During a catch rehearsal, the system extends, plugs in, then detaches automatically when the process is complete. That means no human workers have to enter dangerous areas during fueling or testing. The fueling system itself has been reworked from top to bottom. Pad 2's pipelines use larger diameter stainless steel tubing along with flexible swivel joints that run along the chopstick arms. These upgrades let cryogenic propellants and hydraulic fluid flow more efficiently, even as the arms move or rotate. Dedicated lines now supply steady hydraulic pressure to the arm motors, maintaining strength and control even during full 180-degree movements, something the rigid pipes on Pad 1 couldn't handle. This flexibility allows engineers to rehearse real catch operations using simulated rockets while circulating actual fuel through the system. The result: faster preparation between flights without risking damage to Starship's delicate heat shield. The new pipes are also thicker, up from roughly 20 centimeters to as much as 40 in some areas, to handle the higher flow rates demanded by Starship version 3 and its 33 Raptor 3 engines. It's a practical upgrade that keeps SpaceX ahead of the engineering curve as they push toward fully reusable heavy-lift spaceflight. The first real attempt to catch a returning Starship is expected sometime between flights 13 and 15, depending on how well version 3 performs during its earlier test missions. By that time, Starship is intended to be caught by Mechazilla using strong metal catch pins. Built from the same high-grade stainless steel as the rocket itself, they're designed to take enormous stress without bending or breaking. The reasoning is simple. These reinforced pins can withstand forces that would easily crush thinner or more delicate structures, like the aerodynamic flaps. The catch pin system is a shared feature across both stages of the launch system. Because the Super Heavy and Starship differ in size, structure, and balance, their pin interfaces aren't identical. The supporting hardware, such as the rails, locking housings, and pin designs, must be tailored to fit each stage's specific needs. Operationally, this distinction shapes how SpaceX uses its launch facilities. Pad 1 will likely continue handling the heavy-duty task of catching and recovering the Super Heavy booster, a role it's already proven capable of. Meanwhile, the newly upgraded Pad 2 appears to be optimized for the upper stage. The real challenge lies not in strength, but in precision. Starship's heat shield is covered in thousands of fragile ceramic tiles that protect it during re-entry. Any impact in the wrong place could crack those tiles and threaten the ship's reusability. To solve this, SpaceX engineers explored ways to make the contact points more durable. One solution under test was to remove small patches of tiles where the arresting arms would make contact. During Flight 5, SpaceX flew Starship with those areas exposed, evaluating whether it could survive re-entry without full tile coverage. The result was surprisingly positive. The vehicle held up well, showing that those naked spots could safely handle the stresses of atmospheric re-entry. That success points to a practical strategy: keep the catch zones free of tiles, allowing Mechazilla to grab the vehicle directly without harming the heat shield. For better control, one of the most noticeable changes is its new grid fin configuration. Instead of the traditional 4 fins, SpaceX has trimmed the number down to 3, each one larger, stronger, and more capable than before. At first glance, reducing fins might seem like a step backward, but in practice it's a smart move. Fewer fins mean less drag and less mechanical complexity. With 3 strategically placed fins, the booster now aligns more naturally with both its lower fuel tank and the tower's catching arms. That makes the entire catching and lifting process smoother, quicker, and more precise. The fins are arranged in a distinctive T-shaped pattern, 2 spaced 90 degrees apart, with the third opposite them at 180 degrees. This setup gives the booster exceptional stability as it descends, especially during the high-speed portion of its return flight. Each fin is roughly 50% larger than the earlier design, providing extra surface area for fine control and a stronger grip on the air during maneuvering. The redesign also improves heat management. By mounting the fins slightly lower on the booster, SpaceX keeps them out of the hottest re-entry zones. That not only protects the fins themselves, but also keeps their hydraulic control systems cooler and safer. Reducing weight has been another key goal. For a tower catch to work smoothly, the spacecraft needs to be as light and balanced as possible. Engineers stripped away excess mass wherever they could, especially in the new Raptor 3 engines. These engines no longer rely on bulky external heat shields. Instead, they use built-in cooling channels that circulate fuel around hot components. SpaceX also simplified the plumbing by routing fuel lines inside the engine body and using 3D printing for complex parts. The result? Less weight, cleaner design, and faster production. Each Raptor 3 now generates about 280 tons of thrust, up from 230 tons in the previous version, while remaining 330 kilograms lighter. Multiply that across 6 engines on the Starship upper stage, and the savings add up to roughly 2 metric tons. That lighter frame means the spacecraft can hover more steadily and with finer control during its final approach to the launch tower. Less mass also means less fuel is needed to hold position. The onboard computers can fine-tune thrust more precisely, helping the ship ease into Mechazila's arms with minimal vibration or stress. When the pins make contact, the engines shut down smoothly, no jarring motion, no extra strain on the structure. The catching sequence itself is planned with precision. After re-entry, Starship flips upright and ignites its 3 Raptor engines, using them along with its flaps to slow down and maintain control as it nears the launch tower. Meanwhile, Mechazila's twin arms open wide, guided by radar systems that track the ship's movement. As Starship hovers into position, the tower's sensors align the arms with the catch pins, ensuring a perfect fit. The arms close in slowly, making light contact before sliding into place. Once the pins seat securely in their slots, the engines shut down, and the arms lock tight using hydraulic power, gripping the 5,000-ton vehicle firmly in midair. It's an extraordinary maneuver, but if successful, it will mark a turning point in how humans reuse rockets for spaceflight. Start with the technical issue that delayed Artemis 2 by over a year. When Artemis 1 flew in November 2022, it was an uncrewed test flight. Orion circled the moon and returned to Earth. The mission was declared a success, but engineers found something concerning during post-flight inspection. The heat shield showed unexpected charring and erosion in more than 100 locations. Material that should have ablated smoothly instead cracked and came off in chunks. This happened during re-entry at roughly 25,000 miles per hour, when temperatures exceeded 5,000 degrees Fahrenheit. NASA spent 2 years investigating. The root cause turned out to be gas buildup inside the avcoat material during what's called a skip entry trajectory. When Orion dips in and out of the atmosphere, then skips back up, gases get trapped and cause the material to crack. The issue came down to permeability. When avcoat burns, it produces gas that needs to escape. In this case, it couldn't. Pressure built up under the surface, breaking the material apart. NASA chose not to redesign the heat shield, which would have taken years and added billions in cost. Instead, engineers modified the re-entry path for Artemis 2. The new trajectory will produce less heat and reduce internal pressure. Ironically, another change created part of the problem. Engineers needed clearer ultrasound scans to ensure the heat shield blocks were firmly attached to Orion's body. The older AVCoat was too porous for accurate scanning, so they made it denser for Artemis 2. That made inspections easier, but limited gas escape even further. The revised trajectory can offset that effect by lowering pressure buildup during re-entry. Because the new path narrows timing options, launch opportunities for Artemis 2 are now about half as frequent as before. Where Artemis 1 could launch roughly every 12 days, Artemis 2's window is now cut by about 50%. NASA officials described the mission as significantly more difficult to schedule. Still, the situation highlights NASA's thoroughness. The agency spent 2 full years analyzing every layer of Orion's heat shield to understand the root cause. This slow, methodical process adds safety, but reduces flexibility. SpaceX's Starship program follows a different model. Its ceramic heat tiles, similar in concept to the space shuttles, but built with modern materials, have endured several high-speed re-entries. When problems occur, SpaceX adjusts the design and tests again within weeks or months. NASA and SpaceX represent 2 contrasting philosophies. NASA prioritizes exhaustive review before flight. SpaceX advances through frequent iteration and accepts early failures as part of progress. Artemis 2 is still expected to fly safely, but its delay underscores a larger truth. NASA's cautious pace ensures safety, yet limits adaptability, an area where SpaceX's approach holds a distinct advantage. That doesn't mean SpaceX overlooks safety. The company's motto is clear: human safety is the top priority. What sets SpaceX apart is its fluency, like water. Rather than being rigid, it took NASA's traditional waterfall approach: plan everything in advance, document every step, then build, and combined it with its own fast-paced, hands-on testing style. The result is a hybrid system, disciplined enough to meet NASA's standards, yet flexible enough to learn rapidly from real-world experience. So, what do you think? Is SpaceX's hybrid approach both efficient and sustainable? Share your thoughts in the comments below. While the heat shield issue is a technical problem, the cost issue is existential. According to NASA's Office of Inspector General, each SLS launch costs approximately $4.1 billion. That includes the rocket, ground systems, and mission operations. It does not include Orion, which adds roughly another $1 billion per flight. Total Artemis program spending through 2025 reached $93 billion. That bought one uncrewed test flight and is now paying for the first crewed mission. No lunar landing yet, no permanent infrastructure, just proving that humans can return to the moon using hardware that costs more than some countries' entire annual budgets. SLS is expendable. Every component gets thrown away after a single flight. The core stage, which contains 4 RS-25 engines originally built for the space shuttle, burns up over the Pacific Ocean. The solid rocket boosters splash down, but require such extensive refurbishment that calling them reusable is generous. Even Orion's service module, built by the European Space Agency, is discarded before re-entry. This architecture cannot sustain a lunar program. Simple math makes that clear. If NASA wants to fly 6 missions per year to support a moon base, that's nearly $25 billion annually just for launches. Congress currently appropriates about $25 billion for all of NASA. The numbers don't work. Now consider Starship. Development costs are harder to pin down because SpaceX is a private company, but estimates range from $2.5 billion to $5 billion so far. That includes the entire Starship and Super Heavy booster system, plus ground infrastructure at Starbase in Texas. Launch costs are projected between $10 million and $100 million per flight once the system is operational and reusable. Even taking the high end of that estimate, Starship costs 40 times less than SLS per launch. And because both stages are designed to be fully reusable, SpaceX can fly repeatedly without building new hardware each time. Reusability matters. Falcon 9 first stages routinely fly 15 to 20 missions. Some have exceeded 25 flights. That's why SpaceX can offer launch prices around $60 million commercially while still making profit. The hardware cost gets amortized across many missions. SLS will never achieve that economy. The design is fundamentally expendable. NASA could theoretically fly it more often if production capacity increased, but each flight would still cost billions. There's no path to making SLS affordable at scale. For a sustainable lunar program, you need low cost per flight and high flight rate. SLS provides neither. Starship is designed to provide both. Cost matters, but so does capability. SLS faces limits that Starship doesn't. Payload capacity is the first constraint. The current SLS Block 1 configuration can deliver roughly 27 metric tons to lunar orbit. That's enough for Orion with some margin. Future variants might reach 38 to 45 tons, but those upgrades are years away and not yet funded. Starship, with orbital refueling, can deliver more than 100 metric tons to the Moon. That's not a small difference. It's the gap between transporting a capsule and transporting an entire habitat. Flight rate is the second constraint. SLS can launch perhaps once per year, maybe twice if everything goes perfectly. Production bottlenecks make higher rates impossible. There are only 16 RS-25 engines in inventory, all from the Space Shuttle program. New RS-25 production exists but costs over $100 million per engine. Solid rocket booster segments take 12 to 18 months to manufacture. Starship is designed for rapid reuse. SpaceX already launches Falcon 9 more than 100 times per year. Starship shares many manufacturing and operational approaches with Falcon 9. Once the system matures, multiple flights per week become feasible. Mission flexibility is the third constraint. SLS can launch exactly one payload type, Orion with its service module. The rocket is optimized for that specific configuration. You cannot use SLS to launch cargo separately, build a space station, or support anything other than Orion missions. Starship is a general-purpose transport system. It can carry crew, cargo, satellites, or serve as a space station itself. The upper stage provides about 1,000 cubic meters of pressurized volume, equivalent to the entire ISS. For lunar missions, that volume can be converted into living space, laboratories, or storage. These constraints matter strategically. China is developing capabilities for monthly lunar missions in the 2030s. The United States cannot compete with a system that flies once per year and costs $4 billion per launch. You cannot build a moon base by delivering 27 tons once per year. You can build a moon base by delivering 100 tons multiple times per month. The architecture determines what's possible. Here's the situation NASA finds itself in. The agency has spent $93 billion developing SLS and Orion to return astronauts to the Moon. Artemis 2 will demonstrate that capability in February 2026. That's real progress. But for Artemis 3, the first landing mission, NASA selected SpaceX's Starship as the lunar lander through a $2.9 billion contract. This creates an odd dependency. NASA pays $4.1 billion to launch SLS. Starship does the hard part, landing on the Moon. It provides life support during the surface stay. It ascends back to orbit. Orion just waits in lunar orbit, then brings the crew home. This arrangement makes sense given current constraints. SLS and Orion exist now. Starship lunar lander is under development, but long-term, the logic breaks down. If Starship can land on the Moon, it can also launch from Earth with crew. The capability needed for lunar landing overlaps substantially with Earth launch requirements. Once Starship demonstrates orbital refueling and crew rating, there's no technical reason to use SLS for transportation. Crew could launch on Starship, refuel in orbit, fly to the Moon, land, return, and come back to Earth, all on hardware that costs a fraction of SLS per flight and can fly far more often. Elon Musk has said this explicitly. SpaceX is developing Starship to enable lunar bases and Mars missions. Those goals require capabilities that naturally obsolete expendable rockets like SLS. NASA understands this. The agency has already funded Artemis missions 3 through 5, which commits to using SLS through roughly 2030. After that, decisions will be made based on available capabilities and budget realities. If Starship proves itself over the next few years, the economic and operational case for continuing SLS becomes very difficult to make. Even with political support and jobs in key states, spending $4 billion per launch when a $100 million alternative exists cannot be justified indefinitely. NASA has dominated space-based astronomy since Hubble launched in 1990. That dominance now faces its first serious challenge from the Xuntian Space Telescope, previously known as the Chinese Space Station Telescope. Hubble's primary mirror measures 2.4 meters in diameter. However, while Hubble observes narrow slices of sky, Xuntian acts like a wide-angle camera that captures a whole football field at once, 300 to 350 times bigger than Hubble's view, but can't see the ant's legs as clearly. This design philosophy prioritizes breadth over depth. While the James Webb Space Telescope peers into distant cosmic epochs through a narrow aperture, Xuntian can survey vast regions of sky in single observations. For mapping dark matter distribution, cataloging galaxies, or hunting exoplanets across wide stellar fields, the advantage is significant. The telescope's most notable feature is operational, not optical. Xuntian will orbit alongside China's Tiangong space station and physically dock for maintenance. Astronauts can replace instruments, repair components, and upgrade systems without designing an entirely new mission. NASA possessed this capability during the Space Shuttle era. 5 servicing missions extended Hubble's life and capabilities far beyond its original specifications. That option disappeared when the shuttle program ended in 2011. Xuntian's launch has slipped to late 2026, a line roughly with NASA's Nancy Grace Roman Space Telescope, scheduled for 2027. Roman will provide a 100-fold increase over Hubble's field of view. Impressive, but still 1/4 of Xuntian's degree field of view. This enables China to map vast sky areas more quickly, up to 40% of the sky over a decade. American astronomers have noted these developments with measured concern. China may become the leading force in survey astronomy if Xuntian meets its specifications. NASA has issued no public criticism, but the competitive implications are clear. SpaceX revolutionized spaceflight by landing and reusing orbital-class boosters. China is pursuing a different solution to launch costs: eliminate the need to recover the booster entirely. Galactic Energy, a Chinese commercial space company, is constructing the world's first maglev rocket launch pad, targeting operational debut by 2028. The concept uses superconducting magnetic rails to accelerate rockets horizontally before engine ignition, similar to an aircraft catapult, but operating at far higher velocities. Galactic Energy's verification platform aims for Mach 1+, over 1,200 kilometers per hour. Additionally, lab tests in China, including Hubei East Lake and National University of Defense Technology, achieved 650 to 800 kilometers per hour, Mach 0.65 to 0.8, with 1.1-ton models on short tracks, 400 to 1,000 meters, in 2025, accelerating in 2 to 7 seconds. The physics are straightforward. Rockets must overcome Earth's gravity and atmospheric drag to reach orbit. Traditional vertical launches fight both from the first second. An electromagnetic launcher provides the initial velocity boost using ground-based electrical power rather than onboard fuel. Engineers estimate this approach could reduce propellant requirements by 20 to 40%, decrease acoustic stress on payloads, and enable a faster turnaround between launches dramatically. The concept is not new to American aerospace. NASA studied electromagnetic launch systems extensively in the 1990s under the Maglifter program. The technology showed promise, but required advances in superconducting materials and power systems that didn't exist at the time. The program was shelved to shift priority toward reusable rockets like the Space Shuttle and X-33. China is now positioned to operationalize what NASA abandoned. But Elon Musk also intends to bring back the idea of electromagnetic launch systems, known as mass drivers, to support mining operations on the Moon. These systems would be powered by a constant supply of electricity generated by AI-controlled satellites equipped with solar panels. Once constructed, a mass driver could continuously and affordably launch materials, handling up to 600,000 tons annually. Launched starting in 2015, China's Jialan-1 constellation has 117 to 130 satellites in orbit as of late 2025. Jialan-1 operates in sun-synchronous orbit between 535 and 600 kilometers, positioned to capture consistent lighting conditions for imaging. The constellation achieves global revisit capabilities up to 37 times daily with sub-meter optical resolution. Recent demonstrations have shown satellite-to-ground laser communication at 100 gigabits per second, indicating China's progress in high-bandwidth space links. The constellation's strength lies in surveillance and reconnaissance applications. Jialan-1 can monitor specific locations 10 to 37 times per day, providing video and multispectral imaging across 133 million square kilometers. This capability supports agricultural monitoring, disaster response, urban planning, and military reconnaissance. Starlink's satellites carry no imaging equipment. They exist solely to move data. China has committed over $375 million in government-backed funding to expand Jialan-1 to 300 satellites by 2027. This expansion will increase revisit frequency and reduce the time between observations of strategic locations worldwide. For governments requiring persistent surveillance of regions, borders, or military installations, frequent revisit capability provides intelligence advantages that communication satellites cannot match. This shows that China's government-backed program emphasizes capabilities that provide state-level advantages in monitoring, reconnaissance, and strategic awareness. Meanwhile, American commercial space emphasizes services that generate revenue from millions of customers. China has tested a robotic system designed specifically for asteroid mining operations. The device resembles an insect in form. Multiple legs anchor to the asteroid surface, while drilling mechanisms extract material. The design addresses a fundamental problem. In microgravity, traditional drilling creates equal and opposite forces that push the spacecraft away from the surface. The anchoring system allows the robot to maintain position while drilling, then transfer extracted material to collection systems. China has conducted tests using simulated asteroid material in microgravity conditions. Asteroid mining remains speculative economically. No nation or company has demonstrated profitable extraction of space resources. The technology development is significant regardless. If asteroid mining becomes viable this century, China is positioning itself to compete. American companies have pursued similar concepts, but few have progressed to hardware testing. This brings us to whether China's space program will soon equal that of the United States. The answer is probably yes across multiple critical domains. The transformation began with a deliberate policy decision. In 2014, the Chinese government issued Document 60, authorizing private companies to license government space technology and allowing private capital to fund civilian space infrastructure. The arrangement includes a requirement: private companies and academic institutions must share new technology with the military when ordered. This framework created a unified ecosystem where commercial innovation serves national strategic objectives, eliminating the boundaries that separate civil, commercial, and military space activity in American policy. The results have been extraordinary. Annual investment in Chinese commercial space activity grew from $164 million in 2016 to $2.86 billion in 2024. A 17-fold increase in 8 years. More than a dozen private launch companies have raised over $3 billion since 2020, many developing medium-lift vehicles comparable to SpaceX's Falcon 9. China now operates 6 spaceports with ground systems scaling to rival international competitors. Regional innovation hubs in Shanghai, Beijing, Chengdu, Xi'an, Guangzhou, and Jinan bring academic researchers, government scientists, and private companies together in coordinated clusters that accelerate development. The strategic implications extend beyond China's borders. The Belt and Road Initiative has spawned more than 80 space projects abroad involving satellite manufacturing, ground stations, and data-sharing agreements. This network erodes American influence in regions where countries once looked primarily to the United States for space technology and partnerships. China is building dependencies that will shape international space cooperation for decades. Operational capabilities tell the story more clearly than budgets. The Tiangong space station is positioned to become the world's primary hub for activity in low Earth orbit after the International Space Station retires in 2030. Unlike NASA's Artemis program, which has suffered repeated delays, China continues hitting milestones on its roadmap for lunar and Mars exploration. The country's lunar sample return, rover operations, and plans for permanent bases proceed with disciplined execution that American programs have struggled to match. The key takeaway is acceleration. Experts believe the United States remains ahead today in numerous space domains, but China is advancing rapidly and is positioned to overtake America within 5 to 10 years without decisive action. At least America still has a secret weapon: SpaceX. Without SpaceX, Chinese launch activity would already dwarf American orbital operations. SpaceX's 2025 performance demonstrates what private innovation can achieve. The company targeted and nearly reached 170 Falcon launches, shattering global records with 16 launches in May alone and averaging 15 monthly by mid-year, more than all other nations combined. So far, Starship conducted 11 test flights, including tower catches and an initial test transferring 10 metric tons of liquid oxygen between tanks, validating technologies that could revolutionize access to space. As of the end of October, SpaceX deployed more than 2,500 Starlink satellites, contributing to over 9,300 active satellites in low Earth orbit as of late 2025. The huge revenue from Starlink boosts SpaceX's valuation up to approximately $800 billion. SpaceX's mission manifest extended beyond its own constellation. The company launched NASA's Europa Clipper, conducted ISS crew and cargo rotations, supported private lunar lander missions, and launched satellites for competitors, including Amazon Kuiper, AST SpaceMobile, and OneWeb. This capacity to serve customers across commercial, civil, and international sectors secured American commercial dominance, while China focused on fewer, state-led missions. On December 18th, President Donald Trump issued a pre-holiday directive calling for American space superiority, which includes returning to the moon and placing the American flag there before the end of his second term. This new mandate increases pressure on NASA's leadership, now guided by billionaire astronaut Jared Isaacman. His task is clear: to reform NASA's long-standing inefficiencies and steer it toward faster, more effective progress. For more than a decade, NASA has remained committed to its own approach. The Orion crewed spacecraft paired with the Heavy-Lift Space Launch System rocket. The SLS, derived from space shuttle technology, has been in slow development since 2011. Some of its core hardware, including the RS-25 engines and solid rocket boosters, dates back even further to earlier projects such as Ares 1 and Ares 5 in the mid-2000s. By 2025, the SLS rocket alone, excluding the Orion capsule and supporting infrastructure, will have cost roughly $31.6 billion. When combined with the broader Artemis program, total spending from 2012 to 2025 is expected to exceed $93 billion. These delays and rising costs pose a serious challenge to both Artemis's long-term viability and the President's objective. As a result, a move toward commercial alternatives is becoming increasingly likely. That discussion inevitably centers on SpaceX, whose spacecraft and launch systems, especially Starship and Dragon, have drawn wide attention. The successful Crew Dragon mission to the International Space Station in May 2020 proved that a privately developed spacecraft could carry astronauts safely and at a fraction of the cost. NASA awarded the Dragon contract in 2014, and only 6 years later, SpaceX launched astronauts into orbit for roughly $3 billion in total program costs. By comparison, NASA's Orion program has consumed more than $23 billion through 2025, with each launch, when paired with the SLS, costing around $4 billion. SpaceX's achievement showed that a well-led private company can deliver results once thought possible only for governments. It also demonstrated that innovation and efficiency can thrive in a competitive environment. The reusable Falcon rockets, once dismissed as unrealistic, now represent one of the greatest breakthroughs in modern aerospace. Dragon is not only more affordable than Orion, it is also much lighter. Dragon weighs about 9.5 tons, while Orion comes in at roughly 26.5 tons. Orion's excess weight reflects years of shifting directives and changing missions from different administrations. At one point, it was even designed for travel to the asteroid belt. The result is a spacecraft that became an elephant instead of the racehorse NASA truly needed. To play a role in the Artemis program, Dragon would need only modest upgrades, enhanced life support systems, a stronger heat shield, and improved communications, adding about 2 or 3 tons at most. Even then, it would remain a nimble 12-ton craft, far lighter and more practical than Orion's 26.5-ton design. Although the Dragon capsule weighs only about 20% more than the Apollo command module, it offers roughly 50% more internal volume, making it more than sufficient for lunar missions. Unlike NASA's Orion, Dragon doesn't require an SLS rocket to reach the Moon. SpaceX's operational Falcon Heavy can deliver it to low lunar orbit along with a fully fueled return stage, removing the need for the proposed Gateway station altogether. In contrast, the SLS lacks the capability to send Orion into low lunar orbit with enough fuel for the return trip. To compensate, NASA plans to build the Gateway, a small station in a high lunar orbit, as a way station for Orion. However, traveling down to the Moon's surface and back up to the high Gateway orbit would demand a lander carrying nearly twice the propellant needed for a direct mission from low lunar orbit. This complicated, costly plan, often criticized as a Rube Goldberg approach, adds billions in expense and years of delay to the Artemis timeline. So how would a Dragon-based mission unfold instead? The concept relies on a series of coordinated Starship launches. One uncrewed lunar Starship would be placed into low Earth orbit, supported by 2 orbiting fuel depots. Only a single crewed Dragon would be needed. Step 1. Preparing the fleet. SpaceX would first launch an uncrewed lunar variant of Starship into low Earth orbit, followed by 2 refueling depots. These depots would then be filled with cryogenic fuel delivered by tanker flights, much like topping off fuel reserves before a long journey. Step 2. Refueling for the lunar flight. Once filled, one depot would travel to low lunar orbit and wait there. The second depot would refuel the lunar Starship still in Earth orbit, giving it enough propellant to complete its journey to the Moon. Step 3. Crew launch and lunar landing. 4 astronauts would launch aboard a Crew Dragon, rendezvous with the fueled lunar Starship in orbit, and transfer to it for the trip to the Moon. After undocking, the Starship would head for the lunar surface, where the crew would spend several days conducting exploration and research. Step 4. Return to Earth. After the mission, the Starship would lift off from the Moon, refuel at the waiting depot in lunar orbit, and then return to Earth's orbit. There, it would reconnect with the Crew Dragon, allowing the astronauts to transfer back for re-entry and splashdown. The Starships could either remain in orbit for future missions or return to Earth for refurbishment. This mission architecture requires 2 in-orbit refueling operations, meaning multiple Starship tanker launches. To streamline the process, SpaceX could employ expendable tankers, allowing for greater payload efficiency and reducing the number of launches to just 3 to 5 per fuel depot. From a technical standpoint, the concept of using Dragon for Artemis missions has clear advantages. It leverages proven hardware and existing launch systems, cutting both cost and time. Yet, the question remains whether NASA and the broader space community are ready to embrace such a shift in philosophy, from government-heavy programs to a more commercial, flexible model. As discussed earlier, integrating Dragon into the Artemis framework would require several key upgrades. The capsule was originally designed for operations in low Earth orbit, and its current systems reflect that purpose. In its present form, Dragon's life support capability is limited to about a week unless docked to a station, while Orion's system is built for several weeks of independent operation in deep space. Another limitation lies in re-entry protection. Dragon's heat shield, optimized for orbital missions, might not withstand the higher temperatures and pressures encountered when returning from lunar velocity, known as escape velocity. Orion's heat shield, by contrast, is specifically engineered to survive the extreme conditions of re-entry from beyond Earth orbit, giving it the durability required for planetary missions. Orion also offers twice the pressurized volume of Dragon, providing additional room for equipment, consumables, and crew comfort during extended missions. This larger habitable space offers a practical advantage when missions stretch into weeks rather than days. Communication capability marks another point of distinction. Orion's systems are designed for long-range contact, capable of maintaining a reliable link with Earth at lunar distances and beyond. Dragon's communications suite, by design, supports low Earth orbit operations and would require significant upgrades to handle deep space missions. Still, Dragon retains one notable advantage: crew capacity. Its cabin is designed to accommodate up to 7 astronauts, the same as the Space Shuttle, though NASA currently limits ISS missions to 4 for safety and additional cargo room. Orion, emphasizing endurance and redundancy for deep space travel, is optimized for a 4-person crew. This efficiency in Dragon's design stems from its modern engineering philosophy. The use of lightweight, foldable cloth seats mounted directly to the capsule's pressure vessel maximizes usable volume within its compact 9.3 cubic meter cabin. In many ways, Dragon represents the next generation of human spaceflight: leaner, simpler, and more adaptive to evolving mission requirements. Over the years, SpaceX has proposed several Dragon variants aimed at missions beyond low Earth orbit. Most of these designs remain conceptual or were ultimately set aside in favor of Starship, but they demonstrate the company's long-term vision for deep space exploration. Each builds upon the baseline Crew Dragon platform with targeted modifications for lunar or Martian environments. Red Dragon. Announced in 2016 and cancelled 2 years later, Red Dragon was an uncrewed version of Crew Dragon designed for Mars landings. It planned to use Super Draco engines for a fully propulsive descent and landing, eliminating the need for parachutes. The vehicle was intended to deliver roughly 1,000 kilograms of cargo to the Martian surface while testing critical entry, descent, and landing technologies for future crewed missions. Dragon XL, developed under NASA's Gateway Logistics Services contract within the Commercial Lunar Payload Services program, Dragon XL represents a larger, cargo-focused evolution of the Dragon line. Designed to launch aboard a Falcon Heavy, it can carry approximately 5 tons of supplies to lunar orbit every few months, starting in 2025. With an extended trunk and upgraded propulsion systems, Dragon XL is built for long-duration operations in deep space, serving as a key